and Agricultural Engineering in the University of Kentucky, USA. He has completed his MS Faculty Fellow for Student Success, John Deere Teaching Award, UNL Parents Association and Teaching Award, ASABE Superior Paper Award. He has published many research papers and review papers in reputed journals. He has guided many PG and PhD students for their research work. Dr. Santosh has presented and acted as invited speaker in many webinars and conferences. Also, he is working and has worked as principal investigator and co-principal investigator in about 36 externally funded projects and many internally funded projects. Now, without taking much time, I request Dr. Santosh sir to start delivering his lecture.
Thank you, madam, for your kind introduction. So good morning, everybody. How are y'all doing? Good? All right. Let's get started. So today I'm going to focus on field robotics for climate smart agriculture. So how can we use robotics as tools for climate smart agriculture? So some of the pictures you see here on the screen are some of the robotic test beds that we developed at University of Nebraska, Lincoln. So how many of you heard about Nebraska before today? Okay, so you must be ag engineers, agriculture engineers, the Nebraska Tractor Test Lab report, right? So if some of you don't know, so Nebraska is the home for the Nebraska Tractor Test Lab, which is 100 years old. So it was established in 1920. So every tractor that gets sold in Nebraska gets tested for performance. So if a tractor company says their tractor horsepower is 100, so we test that and make sure the claim is correct so that farmers are benefited by that report. And we generate those reports, and those reports are used worldwide. And again, the primary goal for the Tractor Test Lab is to protect the farmers. So they can go buy a tractor, but if it's not performing well, it's of no use, okay? So I will, let's see if I can, okay. So here's the overview of my presentation. So I'll talk about role of robotics for climate smart and conservation agriculture practices. Swarm robotics. So this is a concept where instead of using one big tractor, can we use multiple small tractors or robots? And then the Nebraska robotic test beds. So over the last 6-7 years, I've developed many robotic test beds with my team. So I'll be talking about that. And then tractor power characterization and electrification. Is electric tractors coming? Are electric tractors coming? Electric tractors is a interesting topic, so I'll talk a little bit about the data we collected to assess whether electric tractors are feasible or not, okay? And then the future of farming a little bit, and then next generation workforce. So today we are here to learn about robotics in agriculture. So how do you train students at the intersection of agriculture, robotics, and AI, right? So that's a really, really tricky challenge. You know, the next generation, we all know, we are going to use more and more technology in the future. So, but then how do we change our curriculum so that we can adapt our curriculum to prepare the next generation workforce, okay? So we'll talk about that. And finally, since it's 1.5 hours, I don't want you to listen to me for 90 minutes, okay? So I'll stop at 1 hour, and then we can have a Q&A, okay? So because I don't want you to sleep, all right? So I want to start this definition of conservation agriculture. So if you think about conservation agriculture, one of the first thing is minimum soil disturbance. So we should not disturb the soil. And then biodiversity, we need to have multiple plant species, right? And also permanent soil cover. So if you have permanent soil cover, we can avoid soil erosion. So ultimately, your conservation agriculture practices is a lot about protecting the soil and the soil health. So if it's like 1 or 2 acres of land, it's easy, right, to manage. You can have multiple plant species. You can have cover crop if it's 1 or 2 acres. But what happens if it's thousands of acres? So in Nebraska, the average size of the farm is 800 acres. Here, how much is it here? 4 acres? Yeah, around 4 to 5 acres, right? So in Nebraska, the game is different. It's like 800 acres of lands. So if you have to do conservation agriculture practice or climate smart agriculture practice, we have to have mechanization. So I work a lot with the farmers, and most of my research actually is geared towards how to help farmers with technology tools. So I know a farmer and his brother, they farm 8,000 acres. Guess how many workers they have? 3 full-time workers, that's it. Only 3 people manage 8,000 acres. So I'll show you some of the equipment they have. They have some of the largest equipment. So my undergraduate degree was in mechanical engineering, and when I went to the US, I was like, wow, these guys use a lot of machines. So that's how I got into agriculture engineering, okay? So the point I'm trying to make is, in Midwestern agriculture, that's where I come from, Nebraska, Kansas, the farms are very large compared to Californian agriculture. Californian agriculture is more specialty crops or vegetable crops. But in the Midwest, Nebraska, and then Ohio, Kentucky, Kansas, there are very large farms, and mostly we do corn or maize, soybeans, wheat. That's it. So millions and millions acres of this. And then a lot of precision agriculture technology is used, okay? So now, if you think about precision agriculture, everybody heard about precision agriculture, correct? So in the context of US agriculture, precision agriculture is per acre site-specific management. So if you're applying fertilizer, so how many kilograms per acre or how many liters per acre of fertilizer. But I think with robotics, we have an opportunity to treat individual plant. Okay, so if we, let's say in this slide here, we can manage weeds in a very targeted way. And we can also, using robotics, we can have multiple crop species in the same land, in the same field. Do we do multiple crops in the same field here? Yes, right? So, but in the US, it's hard. Because without mechanization, you cannot do that. Okay, so how do we scale these climate smart agriculture practices, like multiple crops in the same field to thousands of acres, is one of the goals of my research. So we had a lot of issues with nitrogen leaching in the United States. So that's why it's very important to use robotics and targeted management to reduce fertilizer runoff. So this is one of the examples where we had fertilizer runoff. So let me tell you a story of Charlie, the corn plant, or the maize plant. So today with all the technology we have, so today we use drones, we use IoT, right? So with all these technologies, we know a lot about this corn plant, so we know a lot, okay? And then there are weeds, and then with the IoT, everybody know IoT, right? So Internet of Things, if you have good connectivity. Actually, the connectivity I feel is better in India than in the US. So I manage a 300-acre farm in the US as part of research. We don't have wireless connectivity, not even a cellular connectivity. So it's very bad in the United States, probably because of the geographic area, okay, and population density. So, but with IoT, I would say in the future, right, you could be getting a call, text, or a tweet from your corn plant, okay? So the point I'm trying to make here is we have a lot of data today. And that's why we want to use AI techniques, edge computing, cloud computing, to take that information to actionable intelligence. So what I'm going to focus today is, okay, you have the AI models, you have the data, so then what? Who's going to take action in the field? So that's where I feel like robotics can be useful, right? That could be your high-tech farm helpers, if you want to think about it that way. So that you can give it the actionable intelligence, and the robots are the ones that are going to execute it in the real time. So I'm going to talk about assuming that we have AI, we have figured out the data, now you give a prescription map to the robot and say, okay, robot, go and do this. So that's what I'm going to talk about today, okay? So, by the way, Charlie is not alone, all right? So it has a lot of friends. So you have like 6 million plants in a 200-acre field. So now how do you manage all this? So that is the reason why today we call precision agriculture as what? Digital agriculture. So there's a lot of zeros and ones that need to be, crunched, and we need to convert this into actionable intelligence, okay? So why not send a robot, correct? So that it can go and take care of the plant. So even though this robot looks very cartoonish, it has decision making. It has eyes to look at obstacles and avoid. It has connectivity. It has multiple types of robotic arms, right? So that it can either spray or do mechanical removal of weeds. And still today, with all the technologies we have, a farmer cannot just go and buy a robot like this, even in the United States. It's not there. So that's the focus of my research, is how do we develop these multi-purpose robotic tools so that we give it the prescription map, right? So that it can go and do the operations in the field. Okay, so think about it as a high-tech farm helper, okay? But where we are today, so this is an example of one of the tractor we recently tested at Nebraska. So it's a 600 horsepower tractor, almost 30-ton weight. Our very heavy equipment bad for the soil, like soil compaction. If you don't have good amount of tires and soil contact area, we'll have major soil compaction issues. If you don't have a, so if you think about tracks versus wheels, it's important to select. So a lot of tractors now have tracks instead of wheels to reduce the soil compaction, okay? So, and also something else is to think about is very important, which is mechanical life versus technical life or technological life. You can see that mechanical life is not equal to technical life. So this tractor here is designed for 40 years, 40. So they use only for 500 hours a year. So they designed for 20,000 hours. So it's like 40 years on the farm. That's the mechanical life. How about technology life? 40 years? Every year technology changes, right? So maybe 7 years at the max. By that time you have new sensors, new software. So even though you have a very good working mechanical machine, it's not smart enough. So that's why as roboticists, as engineers, we need to figure out how do we coincide this mechanical life to technology life, okay? So maybe 7 or 8 years is a good number to aim at. So this is another farmer I work with. It's a 48-row planter. So you can plant 80 acres in 4 hours, maybe. Okay? So very wide equipment, you can see. And then very wide sprayers. These large machines and wide equipment are great. Remember I told you 2 brothers operate 8,000 acres. They use this type of equipment, right? Because you can really get a lot of things done. But what happens if your field is not square and it's irregular shaped? So what is happening most of the time if you have a very wide planter? It's a lot of turning instead of spraying. So that's why we need a lot of electronics, and it's called section control or individual nozzle control. So if you think about this wide sprayer, as it is turning, the outside goes faster, right? And the inside goes slower. So the outside is covering a lot more area, so your application rate needs to be higher than the inside. So that is the reason why now the technology in Precision Ag technology is section control or individual nozzle control. So we need all these electronics if you have a very wide equipment, okay? So you can see only green areas are where we were within plus or minus 10% of the target rate. Everywhere else, you're either over-applying or under-applying, okay? So that's why the Precision Ag technology section control is very important. So now a little bit about where we are going. So on the left side, we have the harvester, and then, so for some of you have not seen like typical cornfields and harvesting equipment, a lot of times farmers try to unload the combine on the go, because the grain cart tractor is always going next to the tractor, and today this grain cart can be driverless. So once it is synced, you don't need to have an operator in the grain cart tractor, okay? So on the right side you see that's by Case New Holland. Anybody heard about Case New Holland? CNH is a tractor company. John Deere, Case New Holland. So they have this robot platform. So what can you see? What's the big difference there on the right side? Doesn't look like a tractor, right? And it does not have a cab either. So if it's going to be driverless, right, why do you need a cab? Okay, so as you can see, so we are slowly transitioning away from a traditional tractor. So I would say 15 to 20 years from now, tractors might not look like tractors. They'll be totally different looking machines with the option of no cab, okay? So it's not just researchers. Again, researchers do like crazy ideas, correct? But it's the industry too. The industry is also working on this, okay? So we all know drones are used heavily. I would say in the last decade or so, we focused a lot on imagery, and still today we focus a lot on imagery, right? So drones are great because when you go out to the field, you can get a bigger picture of what is happening in each of your fields, right? So even though drone technology is great, what is the most difficult part with drone technology? Taking that raw imagery to an actual usable data or actionable data. So I talk to a lot of farmers. A lot of farmers don't want to do this because, okay, I can fly a drone. They fly a drone to take nice videos of their other equipment, not because to get the images or data, okay? So, but today they're also used for spraying because drones are becoming bigger and bigger, so we can actually do the spraying. So I think in the Indian context, drones are great, right? 2 acres, 4 acres, you go, fly, spray and come back, because drones can be there for like, what, 20 minutes at the max? But if you want to cover like thousands of acres, you need to do multiple trips, okay? So that's the reason why we need bigger drones in the US context, okay? So I think there are great tools in India here. So now, with this in mind, I just want to focus a little bit about history, right? So why do we call tractor power horsepower? Because it's literally, back in the day in the US, they used horses. In India, we use ox, right? Or bulls, right? So, but in the US, they use horse. Literally, if a tractor is 100 horsepower, that has power of 100 horses, okay? So 1920, that's one of the first tractor that Nebraska Tractor Test Lab tested. It's a John Deere Waterloo Boy. Fast forward 100 years, we have very sophisticated tractor, almost semi-autonomous, you know? So today, in today's tractor, the operators just sit there and monitor for problems. They don't control anything because it's auto steer, it's guided by the GPS. So for example, if they're planting, at the end of the row, they turn around. That's when the human operator turns it around. In some cases, you can add more technology so that it can also do turn automatically as well. So today, operators are almost like babysitters. You heard about babysitters? Nannies. So they're just sitting in the tractor watching for problems. Everything else is autonomous, you know. The tractors are controlling themselves. Okay? So now the question is, why to have the operator in the tractor cab? Why not remove the operator so that the farmer can do other things? If he has animals, he can take care of animals while the tractor is planting itself. So this is where it's important, you know, for a lot of climate smart agriculture practices, we're talking about integrated systems, right? We want crops, we want animals, we want to use manure as natural fertilizer, but it's very hard. Like if you think about how much labor you need, if you have a very heterogeneous system, if you have crops, animals, then it's very hard for just humans to do it, you know, so that's why we need robots. So if you have a driverless tractors, planters doing automatically, the farmer can do other things, okay? So now, next generation, right, in 2040, how does this equipment look like? You can see the transition now. So in my view, I think we have reached a peak on how big the tractors can get, even in the US, because they are so hard to manage, take them from one field to another field. Soil compaction is an issue. So because of that reason, I think the tractors might become smaller and smaller. So this is one of our vision. This is how the robots or tractors could look like in the future. So some are smaller robots that can go in between the crop rows. And the one on the right side is, we call it as a flex row robot that we designed and developed at Nebraska. So it's a 60-horse, multi-purpose robotic platform. Okay? So this is how the future of tractors could look like. Okay? So these are all the test beds that we have in Nebraska. And as you go from the top to the bottom, the complexity increases. Okay? So at the top is our inter-row robot. It's a small robot that can go in between the rows of crop. And in between the rows of crop, when the corn or maize is very tall, you don't have a good GPS. So that's why we are trying to use laser sensors by detecting the line of crop stand and navigate in between. Okay? And then we have the smaller robots. You can see, I'll talk a little bit about each of these robotic test bed, but the point I'm trying to make here is the robots will be of different types and different complexities. One robot will not be solving all the problems. Even though our goal is a multi-purpose robot, we still need to divide that in terms of complexity. And also the big thing, yeah. 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 Okay. Other than the images, sure. Actually, I use one of the robot to take actual measurements in the field. Like we could have, for example, robotic arms, right? So they're using it to pick tomatoes, pick apples, but you can also put sensor probes so that you can take actual measurements. Yeah, make sense? Yes, yes. Yeah, sure. Oh, I see what you're saying. Okay, for it to work autonomously. Yeah, that's a very good question. Like, think about like all the autonomous car field. Have you been following it? Like Tesla is claiming they want to be autonomous forever, and I knew it would never happen. So we are there 98%. To get to the 2% is very, very difficult, you know? So LiDARs, cameras, IMU, and GPS. We need all these. But at least in the farming, we have an advantage, right? The population density is not there. So we can create virtual field boundaries. It's easy to create an autonomous farm than a autonomous car on the road. Yeah, yeah. Okay? Yeah, I'll give you some examples of sensors we are using for autonomy. I call these robots still as supervised autonomy. Yes, they're not fully autonomous. Full autonomy, we are not there. We'll take at least 10 more years for full autonomy, in my view. Okay? Excellent, excellent. Yeah, excellent question. Yeah, so in my view, supervised autonomy is what I say. If someone says something is fully autonomous, I want to review it thoroughly. It's not there yet, in my view. So at the bottom you see I have drones as well. So one of my research program, we are looking at fully how to make drones autonomous. So not just imagery, but how do we make it autonomous? So that's one of the goals. So now actually there is evidence in industry that people are using these swarm robots. So when I say swarm robots, so instead of that one large 600 horsepower tractor, you can use 10 60 horsepower tractors. Okay, so the advantage is that if you have a small farm, use only 2 of these. If you have a large farm, use 20 of these. Okay, so that's the idea. So you can easily scale the technology, by number. Okay, 2 versus 20. Large farmer used more robots. Small farmer used only, let's say 2 robots. If I said this 20 years ago, everybody would be laughing, right? Well, if you have 20 robots or 20 tractors, you need 20 operators, right? Not the case today. So with some autonomy, right? So one person can manage 20 machines, supervised autonomy. So you give it a path, it's planting, but someone is monitoring, how these machines are working. In case if there's a problem, then they'll go and attend to that problem. Okay? So there is evidence in industry. For example, this company here is called Sebanto Ag. They took the Kubota tractors and made them fully autonomous, and they planted more acres autonomously or supervised autonomously than anyone so far in the US. So there is another example, excellent example from Australia. So this is called a swarm farm, and they use these multiple robots to actually do spraying and fertilizer application. Okay? So again, it's not just a researcher exercise, it's actually happening on the farms today. Okay? So now, transitioning to robotics is very important. Okay? So if you farmers, let's say they're using this big equipment, there is a reason why they're doing it, right? So one of the reasons why you need big equipment, especially in Nebraska, is you have 15 days to cover 6,000 acres. How are you going to do it? And with the climate change, that 15 window is getting erratic. Okay, so that's why we need to be very nimble on how we do things. So in that 15 days, if it rains during the planting season, is it a good thing? In the US, no, because tractors cannot go. You'll compact the soil, and the tractors will get stuck. Okay, so because of the big equipment, right? So that's the reason why it's important to know when you're transitioning to robotics, do you go with a machine like this? Again, this is the DOT platform I showed you earlier. Or do you go with a machine like this, or something like this, like a toy tractor? So the problem with the first at the top is they need a specialized implement. They need a specialized planter. So if I am a farmer, I invested in a nice precision planter, I cannot use that robot. So I like the middle one better because it's like a regular tractor. You can attach different implements. So I think that's very important from the farmer perspective. If you're going to go do fully autonomous, or if you want to adopt robotics, how would you do it? So the bottom one is, it's more for research purposes. I don't know if it will have a real value for farmers. Okay? So transitioning to robotics is important, and farmers will be the best people who can provide feedback whether it will work or not. Okay? So always having farmer in the loop is very important. So again, with the idea of field scale neutral solutions, meaning if you have a small field, use only 3 of the machines. If you have a big field, you can use, more number of machines. So you can scale the number up and down. Another important example I will give you is swarm robotics, or using multiple robots is also a good risk management strategy. The reason is, let's say that 48-row planter has a technical issue or a GPS problem and it's stopped. Your whole planting operation is stopped. But if you have these 10 robots, if one is down or one is not working, the remaining 9 are working, right? So that's a good risk management strategy. And also I was talking to you about, the soil, and in that, let's say 15 to 20 day time window, if the soil conditions are not ideal because there was rain, the smaller machines can still go through and do some planting, so that's also an advantage. So I think that is the reason why I say, like, we could explore robotics as climate smart tools, for doing agriculture in extreme environments in some cases, okay? So again, we can use multiple robots, but it's not easy, right? So how do they communicate with each other? For planting operation versus, so baling is a big operation in the US after biomass baling. Anybody heard about biomass baling? Yeah, that's huge. Yeah, that's huge because of animal agriculture. Like Nebraska is a beef state. It's a lot of cows there. So we need to bale the biomass so that you can save it for winter and you use it as feed for cows, okay? And even for dairy. So if it has a baling and picking operation, the coordination between the robots is different from planting operation, okay? And the coordination of these 2 use cases will be different from harvesting. So for example, on the right side, when grain cart 1 is synchronized with the harvester, grain cart 1 is full, then it needs to automatically go out of the way to the field edge to drop off the grain, and then grain cart 2 need to synchronize with the harvester. So as a roboticist, it's important who is the leader, who is the follower, right? So how do you synchronize these tasks? So how does the finite state machines look like? So it's very important to execute this. Again, we're talking about fully or supervised autonomous tractors here. So here's some videos. So this is our smaller robotic platform. Again, this is mainly aimed for researchers. The goal was to sense the microclimate underneath the crop canopy. So it is also doing counting how many plants there are, because emergence is important. For some of you have done emergence studies. It's important to know how much of the corn actually emerged, came up, okay? And then this is our bigger platform. So it's a 57 horsepower hydrostatic transmission, and then 16-gallon gas tank, 14-hour runtime. So we have not done all electric because at this time it's not practical in the field. And I'll show you some data. Maybe diesel over electric is a good option. So that's what we are looking into. But all electric is still not feasible, especially for large acreages, okay? So little details about this platform. So it's a 4-wheel drive. We all know 4-wheel drive, correct? So it's also a 4-wheel steer. So you can go straight. You can turn all 4 wheels 90 degrees, and it can go sideways. So the big advantage here is we can save a lot of turning time. Because in farming, if you want to save on field efficiency, you need to reduce non-planting time. For example, if it's a planter. So one of the big contributor to non-planting time is turning at the end of the rows. So instead of doing a big bulb turn, you can just go sideways. Easy parallel parking, right? So think about that. Parallel parking when you're trying to do, if you can steer all four wheels, it's easy to parallel park, okay? So for any robot, you need to have a good obstacle sensing and avoidance. We have a very basic sensor, and it always works. We actually started with a camera, Raspberry Pi, this and that, but then this need to happen in real time. If it sees an obstacle, it needs to stop. So that's why sometimes it's better to see what is the industry solutions out there and how can we integrate that onto a robot, okay? So this is a good sensor that works great. So as you can see, we're testing this on a very basic obstacle, and it stops when it sees an obstacle, okay? So one of the first things we did with this robot is phenotyping. Anybody work in the phenotyping area? Yeah, phenotyping, yes. So field phenotyping is very important to look at the physical characteristics of the plants. So what are the growth characteristics of certain varieties of plants. So here, this is a soybean field. So and we are going through the crop and looking at the height. And you can see we have an RGB camera, thermal infrared radiometer, fiber optics cable. So we're collecting all this data as we are going through this field, 3 rows at a time, okay? So you can see here, this is another type of field, and I'll pause the second video here. Oh. Okay, so you're going through the field, you're looking at the crop, height, and all other parameters, but you can see there's also a camera hanging, so that's a camera hanging with cables. We have 4 poles, and this camera is suspended. We can move that camera anywhere in that 1 acre plot. So we have this field phenotyping facility. We can move this camera anywhere, just like during cricket or football games, there's a camera. So we have that camera. But the problem with the spider cam, we call it a spider cam, is it's only for 1 acre. So if you want to, let's say, phenotype here in Parbani, we cannot bring it that. But we can bring the robot. So that's the idea. So we are looking at this FlexRow robot as a mobile phenotyping platform. So it also has, the FlexRow robot has the same sensors as our spider cam, So we can take the FlexRow robot any field and then phenotype that field. Yes, ma'am? How many trades? So, it has a fiber optics cable. I'm not into a lot of sensing, but you can put whatever camera. If you want to put hyperspectral, you can do that too. Yeah. So this mobile test bed is very flexible. So there's no problem with power because it's running with the internal combustion engine. So we are not limited by the power, yeah? So one thing I'll show you is, this is what we were measuring, just the height. So you can see on the x-axis it is days after planting. On y-axis is height of the plant in inches, yeah. Yes, good question. So we have done phenotyping, we have done planting. We want to do spraying and nitrogen application. 360-degree, no. Because of the hydraulic hoses, we can do 180 degrees. Good question, yeah. So, but we are working on an all-electric, diesel or electric one. If it's a fully electric drive, we can do that. So right now it's hydraulic drive. That's why we are not able to do it, yeah. Good question. So you can see here some data, sample data that we collected. The average height on y-axis, days after planting on x-axis, and A, B, C, D are different soybean varieties. So you can differentiate the varieties. So which variety is doing best in that environment. So what happened after like 80, 90 days? It's getting ready for harvest. That's why your height dropped, okay? So your robot can kind of look at this phenotypic characteristics. So we can also get the green pixel fraction because we have the RGB cameras. And using some algorithm, we can get the green pixel fraction. And then you can see, I mean, again, this is the sample data set. You can get the yield prediction, yeah? So drones are great too. You can get similar stuff from drones as well, you know, right? But then if you have a ground robot, you don't have to worry about payload. You don't have to worry about, you know, a lot of training that goes with the drone. Having said that, I also think both ground robots and aerial robots or drones, both are important, okay? So now there's a lot of work going on in the soil health domain today. So one of the big things I see is like ground truthing soil health is very difficult. So that's why I feel like if you have a mobile robot, so we can take the FlexRow robot, you know, so you can do cover crop drilling. So for some of you, anybody heard about cover crops? Yeah, so you keep the soil covered so that you protect the soil. Yeah, exactly. So in Nebraska, we have only one season. It's not like here. Here we have 3 seasons, right? So now the harvest is done in Nebraska. So the ground is just bare soil. Is it good to have bare soil? Exposed soil erosion is a problem, right? So you don't want to keep the soil bare. Because of weeds, we don't have problem with weeds because it's below zero. They'll never come up. Now it's winter, it's snowing, okay? But then the problem is soil erosion. So that is the reason why farmers want to plant cover crops. Not all farmers plant cover crops, but that's a really good climate smart technique. Because if you plant cover crops, and cover crops could be barley, you know, there are like 20 different mixes of cover crops in Nebraska. That is just to cover the soil. That's why they're called cover crops. They're not the main cash crops. It's purely for soil health. But then the problem is farmers don't have time after harvest. Remember, there are only 2 or 3 people working on the farm. There's no labor. So harvesting is very difficult, very time consuming. On top of that, you're asking them to do cover crops, which is just for soil health with no benefit for them financially. So they wouldn't be willing to do that. So if you have a robot that can go drill cover crops, they'll be like, okay, now I don't have to hire labor if the robot is going to do it, and we can pay some money towards it. So that's the reason why when I say robotics as climate smart tools, this is what I'm talking about. So how can we help farmers adopt climate smart practices? By giving these technology tools, we can help, yeah? So here you can see we can use the same FlexRow robot. We can put a soil sampler on it. We already have cameras. We can put air samplers on it. So this will expedite the process of research investigations from agronomists and plant scientists. Yeah? So that's one of the things that we want to do, which we haven't done yet, but that's the potential. So you can see instead of this sensor boom, we can add cover crops to it, okay? Cover crop planters. So now the idea is, after the harvest is done, this FlexRow robot can follow the combine or the harvester and drill cover crops. So there are 2 important things here. One is supervised autonomy, because the combine operator can monitor the FlexRow robot. Is it doing its job or not? If not, he can intervene, right? And the second thing is, we want to do immediately after harvest because you have only 3-week time window before it gets below zero. So you're racing against time to cover large acreages because you need some time for the cover crops to establish, right? Once it establishes, if snow falls, it's okay. But even before if it establishes and snow falls and the ground temperature goes below, zero, then that's a problem. So that's why your time window to get the cover crops in the soil is very short, okay? That's where we can use the robots. So you can see the soil probes. One of the ideas is, can we use these NIR probes and put it on our machine, to collect soil samples? Can we put robotic arms, right, to do in vivo sensing, in situ sensing of leaf without damaging the leaves, right? So those are all the possibilities. You can see the robotic arm here. So it is basically, this is in our greenhouse. So it is looking through the time of flight camera, it's looking at the leaf, and we are sending the robotic arm to sense chlorophyll content and leaf temperature without damaging the plant. So in the future, we can take this and put it on our mobile robot so that we can do it in the field as well. Okay? So now, so we did soil core sampler or soil collection unit for a golf course, but we want to do it also for our farm. You can see the sample here, it's 12 inches, you know, so also air sampling, right? So we can put air samplers on this robot. We can use disease detection. So the bottom picture here is not disease, but this is some work we have done with the wheat spike counting. So you have seen wheat crop. So one of my plant breeders, they are working on a wheat variety that is resistant to high temperatures. So this was in a greenhouse. So traditionally they go and count how many wheat spikes there are to predict the yield. So we're trying to use machine vision techniques. So similar techniques can be used for, you know, disease detection in the future as well. Yeah, non-destructive, yes. So now, yeah, yes, without just with machine vision techniques. Yeah. So here now, we're getting into the core ag engineering. How many of you are agriculture engineers here? Yeah, so core ag engineering, right? Planting, how much power do we need to plant? That's very important. So a lot of times I see robotic solutions. Just because we have a robot doesn't mean we can easily plant with it. It's very important to integrate the row unit, right? So the row unit with the robot, okay? So this is an exercise we did. So if you want to plant corn, with it. So we kind of came up with this design. So we wanted to put the row units underneath the machine here, okay? So you can see that's how the row units look like. So we were trying to do a 2-row unit corn planting, and then, so that's how it looks like. We actually planted corn with this row part, you know, early this year, and the corn came up, so we were happy. So now you all know difference between no-till and till conventional, right? So our goal is no-till planting. So the no-till planting takes a lot more downforce so that we can plant, okay? So in this situation here, you know, we have to look at the robot. Can it actually help with the planting? Does it have enough power? Does it have enough control systems? Because planter row units are very highly sophisticated technologies today, and we need to integrate that into our robot. So a little bit about our robot. It has 10 ECUs, or electronic control units, the LiDAR, the GPS, and one ECU is, actually 3 ECUs are dedicated only for controlling the planter row unit, okay? Anybody heard about CAN bus on tractors? Controller Area Network Bus? Yeah, so it's a communication among multiple ECUs. Like I said, I have 10 ECUs, right? So how do those ECU communicate with each other? Is through this CAN bus protocol. So we have a CAN bus protocol, which is actually industry standard. Every tractor car uses CAN bus communication. So we have the same thing here. So traditional ag engineering stuff. So how much draft force do you need? How much power you need to pull a planter row unit so that we can successfully plant, okay? Like I said, this is a hydrostatic transmission. What that means is your engine is driving a pump. The pump is creating the hydraulic flow, and you're using that hydraulic flow to drive the hydraulic motors. So we have 4 hydraulic motors on each wheel. So we are using hydraulic power to actually drive this machine. So we have to go through all these calculations because we want to know, do we have enough power to plant with 2 row units, okay? So now you can see, so on the right side is your planter row unit. That's where the seed is actually, drops into the soil. But before that, a lot of things need to happen. We need to separate each seed. That's where you see the seed meter, and then there is a seed meter motor. So what's the goal when you're planting maize? It needs to be 2 inches below the surface of the soil, okay? And then 6 inches between each seed. So that's the goal. Whether you're going fast or slow, your planter row unit automatically needs to adjust that. If the soil is compact versus soft, it needs to sense that, okay, in the compact soil, I need to put more downforce so that I can place the seed at 2 inches. In the soft soil, it should not have so much downforce. So all of that is done by that ECU there. So it is sensing all this and controlling the seed meter in real time, okay? So the planting technology is very sophisticated, and then we integrated that into our robot, okay? So now, this is a field that I was talking about. So this is a 300-acre field I manage, and my dream is to make it fully robotic in the next 5 years. And our first step was we planted 2.5-acre field with our robot. So 2.5 acres is not a lot, but this is our first time doing this, okay? So we did this with our FlexRow robot. You can see how much biomass there is on the surface here. So as you can see, the future is here. You have a robot, it's planting by itself. We are still monitoring it, right? It's a supervised autonomy. So things can go wrong. That's why you always need to monitor either using remote dashboard or from vicinity. But at least when this robot is planting, if I have animals, I can take care of the animals as well, okay? And we need to build all the intelligence possible into this robot. So it has obstacle detection avoidance, so it can follow the path, right? So all of that intelligence is built, but still things will go wrong, right? So one of the things that went wrong here was the downforce was not perfect, because that's why we had to put some weights. You see some orange weights at the bottom. So all of this will happen only when you actually do the experimentation in the field. You can have all the theory, all the models, but unless and until you go down into the field and do things, you don't know what problems will arise, okay? There you go, the corn came up, so we are happy, the robot works. I'll show you some more videos later. But one thing we are trying to do is, we're also looking at how much power does it actually need to do planting. We have a standard, ASAB standard, where we can estimate how much power is needed, but that's like 50 years old. Anybody use machinery standards? ASAB machinery standards? Yeah, so it has equations on how to predict how much force is needed or how much power is needed when you're going at certain speed to plant. But then here, we can actually get real data. So ultimately, we're keeping track of how much kilowatt is needed if you're going at a certain ground speed, right? So if you know how much kilowatt, then we can calculate kilowatt hour. Once we know kilowatt hour, we can size the battery, okay? So that's kind of the idea. While we are testing for robotic planting, we're also collecting how much power is needed, okay? All right, one thing I want you to note is, if you look at the tank, it's not very big, seed tank. So after a certain time, it's going to be empty, so then what? So this is a big issue I see with swarm robotics. A lot of research talks about swarm robotics, but they forget that material refilling is important. Okay, so if you have a big planter, it has a big tank, you plant the field, you're done, right? How many of you done planting or spraying? Anybody from the farm? Perfect, right? So you want to go, get it done, and come back, right? You don't want to go back and forth. So, but with swarm robots, a lot of researchers, the problem is they don't think about the logistics of material. That's very important. Because I don't want this robot to go back and forth to refill the tank, okay? So that's the reason why one of the things we are looking into is, can we use drones? Drones are good at covering long distances. It can drop off the seed. And the ground robots are always planting until the mission is done. Okay, because remember, 15 days time window, a lot of acreages. We want these robots to be working 24/7. That's one of the advantage, right? When we say robots or driverless tractors, we want to use them 24/7. But if you don't refill the tank, you're not going to make it happen, okay? Exactly. Nope, nope, nope. So drones are good at something, ground robots are good at something, and we need both, okay? So this is our concept. So when this FlexRow robot is going and planting, the drone can refill the seed. In the future, the FlexRow robot can be applying fertilizer. We could be refilling the fertilizer. We could be refilling the chemicals in the future, also the fuel, right? So this is where we want to use the best of both worlds. Drones are good at something, covering long distances. Ground robots are good at something because no restriction on payload. So that's why we can use the best of both worlds, okay? So now, that's great, right? Drones and ground robots. Think about the complexity of mission planning. That gets very complex, right? So that is the reason why what we are doing is we are using something called Gazebo so that we can plan mission in a virtual environment first. So you can see there's those white little spider-looking things. Those are the drones, and those are the ground robots. So using the Gazebo, we are trying to simulate, can we do this in the virtual environment first, okay? So now, my lab is very applied research. We always want to do real stuff on real drones and real robots. So we got the DJI. This is Matrix 100, I believe. The reason why we got it is there is a SDK, or the software development kit, so that we can put our own computer and make it fully autonomous. So how many of you used Arduino before? Arduino boards, anybody? Yes. Raspberry Pi boards. Some of you Raspberry Pi boards, maybe if you're into ag engineering and electronics. Jetson Nano are more good for GPUs. So we skipped all that, and we're directly using mini PC. We thought that's the best way to do it. Because with the mini PC, you have all the peripherals, all right? And then enough computing capacity so that we can do things in real time, as you can see here. So our goal is to do a PID control so that we can control the velocities in X, Y, and Z direction, so that today's drones, when they see an obstacle, what happens? They'll run into it and crash. So, but in the future, if you want them to be autonomous, it needs to have obstacle sensing capability. And also, what happens if there is no GPS? For some of you fly drones, if the GPS signal is lost, what happens? They'll come back to home, right? So, but in the future, we want it to continue to navigate even if there is no GPS with visual navigation. So we are using cameras so that, it can use cameras for navigation when the GPS signal is lost, okay? So here's one example of a test bed that we have. We build all this. We started with a Cube Orange and Raspberry Pi. Then we realized it's not powerful enough. So we upgraded to this domestically, US drone here, which has a LiDAR. And then we use our mini PC, okay? So again, we want to test our mission planning in virtual environment. The reason is, if you have a ground robot, if your mission plan doesn't work, what happens? It will stop, right? It's okay. How about for drones? If your mission planning does not work, they'll fall out of the sky. So we don't want that, right? So that's the reason why we test this in our virtual environment. This is an environment called AirSim. It's mainly done for drones. So here what we did is we are trying to avoid the obstacle, that nice looking obstacle. It looks so nice, I want to run into it, but so we want to avoid it. Okay, so you can see it will avoid the obstacle there, and then it will basically avoid all the obstacles. It's basically a reactive behavior based navigation. Okay, so now in the next simulation here, so here is there are two drones trying to follow each other. So there is a drone in the front, that's like the leader, and the drone in the back, that's like the follower. Excuse me. So ultimately they have to collaborate. So ultimately they have to be on top of each other basically. Okay? So again, these simulations are very important so that once we are happy with this, then we can port this code onto our physical drones. Okay? So now I'll just show you some videos of the autonomous drones. Again, when I say autonomous, it's supervised autonomy because we are there watching, make sure they don't fall out of the sky. Yeah. Yes. So I have so again, here is where I have a couple of computer science students who are working in my lab. So it's very important, right? To get the best of both worlds. You have agriculture, you have hardware, software. Again, now we're talking about reinforcement learning. So it's very important to bring students from different disciplines. Okay? So you can see the drones here, they're flying. We have given them autonomous takeoff and landing instruction. Once we give the command, it will go autonomously take off and land autonomously. Okay? So that was our first test, you know. Again, it was all in 2023. And the next one was, you can see the drone will take off and go to point B. Is that playing? There you go. So you can see the drone. Anybody wants to take a guess what that corn is? That's the corn the Flextro robot planted. Okay, so that field, Flextro robot planted that field. So we have a nice corn. We actually harvested in November. So now the drone took off autonomously from point A to point B, and then the next step is, you know, doing a ground and aerial robot coordination is the next step. So you can see this drone here is given an instruction to find the ground robot and go and land autonomously. Okay, so this is actually the tractor test lab that I was talking about. You will see a track now. So that's the building. You can see the tractors there. See, it changed course. That is a track at the bottom, our tractor test lab track. But the drone is trying to find, it has a tank on it with some seed. So it is trying to find the ground robot so it can go and land. So it takes some time because we are using RTK GPS, okay? We are using a downward looking depth camera. And also there is something called Aruku marker. It's like a QR code that is on the ground vehicle so that the drone knows, okay, it will positively identify that this is the landing pad. So this is where I need to land. So you can see as you get closer, hey, it was snowing too. So our drones work in snow as well. No. So you can see there at the bottom. So it's analyzing the distance between the drone and the bin at the bottom there on the ground robot. So you see a white piece of paper on the surface on the ground robot. So that's where the QR code or the Aruku marker is. Once all of this is confirmed, only then it will land. There you go. Successful landing. Okay. So there is seed dropping after that. So I would say we crashed this drone only maybe once during this entire thing because of the simulation, you know. So when you're working with drones, it's not always straightforward. There are some crashes, but it was not that bad. So, you know, okay. So that's where ground and aerial robot coordination becomes super, super important. All right. So now autonomy considerations, right? So there are robots and there are AI-enabled robots. What I have shown you so far, we have not used much AI. So AI will not solve everything, and you don't need AI for everything either. Okay. So what you have shown to until now, we didn't use any AI. Okay, except for some wheat identification, but if you want the robot to be fully autonomous, so you need to know, positively identify what are the obstacles or objects in the field. So in the automotive industry, the Teslas and GM, they have been collecting a lot of data on how does the cars look like, how does the traffic lights look like, but how about in the fields? What type of obstacles do we have? At least in Nebraska, we have a lot of cows, right? I think in India we have cows on the roads too, right? So it's autonomous, so we can sell this data set to Tesla. Hey, cows, this is how they look like, use it, right? So the bales, tractors, implements, and on the left side, anybody know what the one on the left side is, at the bottom left? It's the irrigation equipment in Nebraska. It's a center pivot system. So center pivot systems are big. So Nebraska is home to the center pivot irrigation systems. So there are 4 manufacturers in the world, and all of them are in Nebraska. So the irrigation equipment. So if you have seen like crop circles, like circular fields, anybody saw on internet circular fields? So if it is a circular field, good chance that it is irrigated with a center pivot system, because the center pivot system just goes round and round and irrigate the crops. Okay? So we have that equipment as well in the fields a lot. So Nebraska is the most irrigated state in the US. So we use a lot of irrigation. So now the robot, when it looks at the structure, it's really hard to determine what that structure is. So it's hard to train that model. Sometimes it thinks the center pivot is a tractor because it has tires and wheels, you know. So we are working on that because, you know, as you all know, if you need AI, you need a lot of data. So, but we are trying to work on that so that FlexRow robot can be fully autonomous someday. Okay. So, weeds, are weeds a big problem here? Weeds. What is a top weed here in Parbani? Cypress? Okay. So in Nebraska, it's something called Palmer amaranth. Palmer is big. So we can train, you know, any weed if you have good data sets. So one of the things we did is actually grew weeds in the greenhouse, right? Who grows weeds in the greenhouse? But we have to do it for research, right? So, and then we had some problems. They were not growing well. Weeds not growing well. How does that happen? But then we trained these data sets using the deep learning model, YOLO V7. So the idea is, again, like I said, there is robots, then there are AI-enabled robots. So here's a good example of an AI-enabled robot, so that we can spray only the weeds and not the maize, okay? So as you can see here, we are capturing the images in real time and sending this nozzle back and forth so that it can spray only the weeds. So you can see here, so it's spraying only the weeds. And when it goes on top of the corn, it does not spray corn. So you have a downward looking camera for that. So I think this is a great example of innovation that could be used here too. Again, we started with the large, big tractors. Now we are talking about smaller robotic platforms, but much more intelligent. So in real time, you can differentiate between Palmer and corn and spray only the palmer. So if you have a different type of weed, we can train that weed as well, okay? Hey, Parbani has a lot of cotton. Nebraska don't have cotton, sorry. But we did this as an exercise for a robotics competition. So like a student robotics competition, again, workforce, future workforce is very important. So we had computer scientists, we have ag engineers, we had mechanical engineers, all working on this project. So traditional approaches cannot be used because, you know, it's hard, right? So you can see the boxes here and, you know, they're getting detected. So that's why CNN, we just used a YOLO V3 because it was student competition. That's our robot. I just wanted to show you this during the competition. And again, this is a simulated. So this was a simulated board where we put fake corn plants. And then we sent the robotic arm. Okay, so one thing I want to highlight here for this robot is that even though it's very small, it used 3 computers on it. So we have an Arduino board, we have Jetson Nano, you know, we had a Raspberry Pi. So we used a 3D depth camera so that we know the pixels of each of the cotton, how far it is as well, so that we can get the 3D coordinates of the cotton, and then we do inverse kinematics and send the robotic arm to pick it, okay? One of the biggest challenges in my view with robotic picking is they're like 10 times slower or 20 times slower than, you know, people. So it doesn't make sense. Sometimes I feel you need a different cultivar of crops to support robotic picking. Even apples, right? Washington State has done a lot of great work in apple picking, but it is 10 times slower. So, but that's a good challenge for ag engineers and researchers, right? So continue to come up with new ways of.
Yeah, we found a new way that we have a smart cotton picking machines.
Yeah.
Usually picking time is just like a nuclear,
Yeah.
which is this, and then you're taking judgment of the coordinate systems, and then
Yep.
that process is somewhat the processor should be very high.
Yep.
And for the number of balls on the same plant is like 100, it's very difficult. So what we have done is that a cotton pneumatic suction, that cup we have one to make it that cotton suction cup will be having that peaking. So there is another problem that while peaking time there is dust, while when peaking time
Yep.
there is a petals,
Yep.
right?
Yep.
So for that special, I think the filtration, we can use the filter for that case so as to avoid the dust.
Yep.
And we could be able to make the succeed of that operational by use of the smart.
Yep.
That I can show you.
Sure.
And then one of my students is working on the cotton,
Yeah.
by using YOLO.
Yeah.
Here, a robot flow, and then we did the way that the pest, with their identification, there is a big malam, for example.
Yeah.
At the beginning stage, it should be known to that how much of percentage infection is occurred.
Yeah.
At the beginning, if it takes at judgment,
Yeah.
you can have a sense of making a spray at that decision.
Yep.
So that's there with us. Now
Sure.
we are also trying to make the same kind.
Sure. No, that's great. That's amazing to know a lot of work is going on here because it's Parbani, you have a lot of cotton. So sometimes I feel like just like flat apple trees, can we do flat cotton trees, right? I don't know if scientists are like, plant scientists are working on varieties. Can we make a flat one-dimensional cotton tree so that it's easy to pick for the robot? Well, that's the interdisciplinary research, right? You know? Okay, so we are working on gesture control. For example, there is autonomous mode and with a remote. Why cannot be the farmer or operator be the remote? So that we can move the robot with hand gestures. We programmed in 5 or 6 hand gestures right now. And then we did some planting of lettuce. Lettuce seeds are very small. We did that. And then finally, in the interest of time, we have been collecting a lot of data from actual big tractors, how much power is needed for electrification purposes, So I'll just skip these slides here fast. But for some of you who are looking into electrification, look at this number, 2658 kilowatt hour on day 7. 2,600, almost 700 almost kilowatt hour. So a lot of times people are not in farming, they assume it's 8-hour work day, like office, you go and come back. No, right? Farmers work 16, 17 hours a day. So it's not like I'll go and plug in my tractor for charging overnight. No. So 16 hours of 90% load on the tractor. Okay? So that's why electrification is still not a good thing, especially for larger farms. Okay? So that's how big a battery you need to replace one of the tractors that we use in Midwestern farming. So it is not practical right now. Okay?
I come to think that below side surface there is a good energy,
Yeah.
but the upper surface, soil surface, the energy.
So this is the least. This is just planting. So only 2 inches. Not even tillage. This is just planting. Planting is the low draft force, right? So if you go to tillage, this could be like 5 times. Yeah. So I think we're getting close here to finish. I think in the future, robotic tools, we should use them as farm helpers, not to replace farmers, but as tools to help farmers adopt climate smart practices. So you could be seeing ground robots, aerial robots, and also conventional tractors. Okay? And also, how can we do multiple crops in the same field? So with robotics we could do that. And then robotic herding of animals. We are looking into one project where can we use robots to herd cows. So in Nebraska, we have ranches. Anybody heard about ranches? It's like open fields that are like, sometimes it's like 20,000 acres. So where they let the cows go, but then we need to herd them as well, bring them to different locations, provide them water. So we could use robots, solar-powered robots, small ones, to actually herd them, All right. When we talk about future of farming, it's very important to know the timeline, right? Are we talking about 10 years, 20 years, 30 years, 40 years? So let's say 30 years from now, I'm sure we'll be on Mars and Moon. And when people go any place, right, they got to eat. So how do we do agriculture in space? That's one of the projects we are working in. We just had a symposium. We had NASA scientists, people from USDA, just like ICAR in the US. And it has to be greenhouse agriculture, okay? So that's something we are looking into. So it is an example of a student project on the right side. So it's a tabletop greenhouse. So it's an IoT. So can we grow food in closed greenhouses that are tabletop? And also it's a great IoT exercise as well. Yep. So happy to collaborate. Yeah. Yep. Yep. So this is one of the class projects that I did in my class. So and finally, I think agriculture is a truly interdisciplinary field. If you want to come up with farmer-friendly solution, it has to be interdisciplinary in nature and work. We need computer scientists, we need ag engineers, we need plant scientists, soil scientists, everyone come together and work on this problem. And again, I do teaching as well, and I understand the restrictions we have on curriculum. So we cannot teach everything in the 4 years. So, but then through experiential learning opportunities, to these challenges, robotic challenges, maybe we can say an IoT challenge, and pick 2 students from engineering, 2 from plant science, 2 from soil science, and then do projects. I think that's one way to train this next generation of workforce. Okay, that's my team. So that's without them, all of the work that I presented would not have happened. So there are 2 or 3 computer scientists in that team there. So finally, I want to wrap up with this. It's a very powerful image for me. There are 2 20-year-olds here, one from Telangana. You can tell who is from Telangana, right? So one from Nebraska. So that's one of my students from Nebraska. He's also a farmer. Actually, I asked him, why do you use drones? He's a farmer, right? So he's like, yeah, I want to take good pictures and videos of my tractors, but I also want for tax assessment. If they are going to go purchase a new land, they'll fly the drone and see if there are any major problems. So just a good scouting tool. But also recently he bought a DJI drone for spraying. So if the field is small and very irregular shaped field, there is no point in taking a big sprayer. So they'll just use this drone and spray to save time. But the reason why I'm showing is that these guys are the future of farming. How do we train our younger generation is going to be super, super important. I see a lot of young faces here. So it's our responsibility as researchers and professors to train you all at the intersection of agriculture, robotics, and AI, because all of those tools are going to get used. So I think we need to create as many experiential learning opportunities for our students. And I'm here, and I thank the opportunity for VNMKV and the whole team for inviting me here and having an opportunity to interact with you all. Okay? Thank you.
Any questions from the participants?
Yes.
Okay.
Yeah, yeah, yep. Yeah. 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 Yeah, yeah. Actually, like farmers do it right now in the US. Like, let's say I'll take an example of John Deere. If a farmer buys John Deere equipment, so they have a cloud web page or portal with their account. So every time they do an operation, the data is sent to them. So for example, in one field, they have a certain amount of field this year, but they'll also check that data historically. Last 5 years, what is the yield? Last 5 years, how much fuel did I use? So they do that comparison. We have this, but how do we do it in academia and research is through collaboration. So multiple university needs to come together and work on that. Yeah. So the robot I showed you where it was planting, the 300-acre farm, we started to digitize it, meaning anyone can go online and look at the soil properties, look at the yield last 4 years, so that we can make that type of decisions. Can I use the same robot next year? Will it take the same amount of power? Will it, so yeah. I think it's about data aggregation. It's an exercise of data aggregation and presenting it so well that we can take actionable, intelligence. We get actionable intelligence, basically. Yep. Thank you. Yep. Yes, in the US, FAA regulates it. So if you are within like 10 kilometers of a airport, you need to get permission from FAA that we want to fly. But if you're away from there, as long as you have a pilot license, in the US you need a pilot license to do any of this. You need to go through the training and do. I don't know here, do you need a pilot license here? Oh, okay, okay,
Award fees कहाँ
yeah, gotcha. Sure, sure. I think it's about regulation. In the US, it's tightly regulated. So, yeah, yeah, yes. Yep.
Hello, hello.
I can't hear you, so, yeah.
Hello.
As we think about Marathwada region farmer, those who have only 45 acres or 10 acres land, and those who have those farmer not known about AI technology, robotics, drone technology till now. So how can they sustain in the future? Please.
Yeah, thank you. So I think you all heard about the question and cost. Like how can farmers use AI, robotics, and how can they afford? That's an excellent question. So one of the things that we do it as, I showed you a Sabanto, the orange tractors. They do farming as a service. So just like Uber, you don't need to own a car, but you can go in a car. So same way, robotics as a service can be done. So if you're a farmer, I don't know how much money does it cost to plant 1 acre of maize. Do you all, anybody knows how much it costs to plant 1 acre of maize? We need to know that. So then, let's say I'm throwing a random number I don't know anything about. So let's say 5,000 rupees per acre. So can my robot do 5,000 rupees an acre? Or can it do 6,000 rupees an acre? Then it will be attractive to farmers.
Agriculture. So, mass population of India is in agriculture. So, they will go jobless now by robot.
That's a great question. So mass people in, I mean, there's a lot of farming communities. They'll go jobless. In my view, robots are not as smart yet. So we still need people, right? So in my view, we will create better jobs because the farmers can be managing the robots instead of doing really, really hard work. Sometimes I feel very bad that we have all this technology, AI, but then if you have pulled weeds, anybody did weeding with hand? Weeds, removing weeds, it's very hard. I mean, we shouldn't be doing that in my view. We should have a robot doing it and the person can be doing other things to add value. So maybe we can be focusing on value addition, and how to increase, yeah. So that's a great question, very valid question, yeah. And also, I see the demographics change too. So a lot of farmers, sometimes there is no labor because a lot of people are going to better jobs because farming is hard. You can work all year and be in loss, right? So we need to make it more productive and attractive. Like I said, the future generation is all of you. I want to see a day where a farmer wants to send his daughter or son to agriculture engineering because it's practical, profitable, and good versus sending them for computer science degree. That's my dream. Yeah.
Okay. Any other questions? Okay. Thank you, sir.
Thank you all.
Dr. Santosh Kumar.
Thank you, sir. Thank you for being with us. I really thanks to Professor Pitla, sir, for being with us, and he has shown a lot of, dynamic picture of a futuristic farming and opportunities to all young technocrats and then scientist people from agriculture specifically.
Dr. Pitla, sir, has delivered an excellent lecture and has covered many points for robotics in agriculture, starting from robotic seeding and planting up to biomass baling, including field phenotyping, weeding through weed boards with discrimination between crops and weed, robotic cotton pickers, AI for object detection, along with field testing of UAV, UGV collaboration. Hope this lecture will be very useful for the students and researchers present over here. Thank you very much, sir, for a nice lecture. Now I would like to request Dr. Sanjay Pawar, sir, to introduce our next speaker, Dr. Prakash Jha. Pawar, sir, please.
Hello, hello.
Thank you, madam. Our next speaker is Prakash Kumar Jha. I am read here the brief biodata about Prakash Kumar Jha. He is presently working as an assistant professor in agriculture climatology, Mississippi State University. And he did his PhD in crop and soil sciences, concentrations on the crop and soil climate modeling, Department of Plant, Soil and Microbial Sciences in Michigan University. His dissertation title is Agronomical Management of Corn Using Seasonal Climate Prediction, Remote Sensing and Crop Simulation Models. He has a 10-year experience in teaching and research and professional membership of American Society of Agronomy, Crop Science and Society of Agronomy, Soil Science, Society of Agronomy, American Society of Agriculture and Biological Engineer. He has awarded with many prestigious awards like received Young Scientist Award at the International Conference on Climate Change and Agriculture in Jammu and Kashmir, then received Outstanding Postdoc Award at annual meeting of Association of Agricultural Sciences of Indian Origin, then Dr. Delia Co Global Student Scholarship Award in 2019, Best Postal Paper Award and People Choice Award at Annual Environmental Science and Policy Program Symposium at Michigan State University. Sir has published 42 research papers with total citation 729 with H index 12. This is about the brief biodata of Prakash Kumar Jha. Now I request sir to deliver the lecture. Thank you. Now I request the PI, Dr. Gopal Shinde sir, to welcome the Dr. Prakash Kumar Jha.
Good afternoon. Good afternoon. It seems I am between you and lunch. There's a loss of energy. We will have a screen, and then on the screen you see the QR code. If you have a smartphone, please scan through your camera, and then we will interact through this QR code for the next 5 minutes, and then I will come on my topic. So please open your camera and scan the QR code. You will see a link, menti.com. Open that link. If your camera is not working, use www.menti.com and use that code. Okay? If you see the screen, there is a thumb option. Please like. बोलते हैं ना like, subscribe. Yeah, please like. इसको ऊपर कर देंगे screen को. If you like, I see at the bottom here, there is a like button. No, do next. Back, not next. Yeah. नहीं कर पाए स्कैन करने दीजिए. If you are good, if not, then let me know. Open your camera, scan, and then go to the page which is called menti.com. Like, press like. Okay, done. I see a couple of cameras still working. No, not working. If your camera is not working, it means go to your www.menti.com and use that code. Those who came late, please scan this QR code through your camera. Don't use Google Chrome or any other website. Use your photo camera. Open photo camera, scan, and there will be a link on the bottom. You can scan that link and open that page. I see 75% are on. Not voting. I see how many are there. So there is a screen. My screen is here. If you remove my screen, in the corner you will see there is a like button. So how many people have liked? But this is hidden now because of my screen. मेरी स्क्रीन को थोड़ा ऊपर कर दीजिए. Yes. Oh no 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 no. Please don't do that. Okay, I think almost all are done. So please do next. On your mobile screen, you see what is the toughest part of your research. It could be field data collection, it could be data analysis, it could be reading paper. Just write in 1 or 2 words. Whatever comes to your mind. Don't move screen. Whatever comes to your mind. Next. Can you see on the screen? No? Yes, no, yes, no. See, people are replying. So go back to that, menti.com, write the code on the top. 125309992. Okay, seems like this group has complex process for data analysis. This group looks for data collection. Okay. I see 30 responses right now. Digital soil mapping, calibration and validation, instruments availability. Why I'm doing that? Before I start my talk, I want to gauge the audience. I want to gauge the audience what you think and how best we can cater your need. That's why this is 3 or 4 questions I will ask. If you are done, then I will move to another question after some time. Last 30 seconds for you. Okay, next please. On your screen you see what you enjoy the most in research. The first was the most difficult. Now most enjoyable thing in your research. Maybe reading paper, maybe going to the field, whatever. In vitro work. Reviewing, analysis, data collection is enjoyable part, good. Talking to friends, good. Collection of data, operating robot, speaking to experts. Field work, data collection, lab work. Okay, most enjoyable part has conflict with toughest part as well. Good. Field observation. Because since this is a workshop, this is not a direct training program. That's why I want your participation or your engagement. That's why this is an international workshop rather than doing a lecture series. So I want you to participate completely so that I can understand what do you think and accordingly I can change my gear. Looks like this group has data collection and lab work and field work based on font size. Means many people have replied in the field work, lab work and data collection. I think we are good. We can move next, please. Why did you choose to do research in agriculture? Your parents said you can write. Not selected in medical sciences, you can write. Please feel free to write. Just for fun, that's great. No other option. Okay, perfectly fine. Just prior to this event, I was in College of Agriculture with undergraduate students. And I spoke to them close to 1 hour about the career options. So those who wrote not an option, I just spoke more than 100 options to undergrad. Interested in agriculture, work for farmers, just for career, interested in agri. My father is farmer, great. Farmers welfare, occupation, interested in agriculture as I belong from farming, service oriented. Next 30 seconds, then I'll move to next question. Passion, work for farmers to study data management. I like food technology, agriculture background. Okay, I think we'll move now. Next, please. Have you heard of crop simulation modeling? Yes or no? Blank answer. No, no, not to me, to your mobile. Have you heard of crop simulation modeling? Yes or no? Yes, 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 not much more. Yes. No, no. Okay, good, good, good. Couple of more. No, 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 no. Yes, yes. I think yes is more. 38 response, 39 responses, 40 responses. I think we are good 3/4. Next, please. I got to know that you know at least crop simulation modeling. Now on your screen, on my left, if you don't have an understanding or knowledge, move your scale from limited to advanced. If you have understanding, move to advanced. So first is the crop model, second is climate change impact assessment, third is remote sensing, fourth is climate forecast, and fifth is climate change impact assessment. Why I put twice? Deliberately. I will tell you later. I want to match the scale 6/6 in climate change impact assessment. If you are serious enough, you will answer differently or not. Okay. So the mean value at the bottom of the class is less than 5. It means I need to explain about these things in research. If mean value is more than 5, it means you made my work easy. Surprisingly, for climate impact assessment, twice there is a different rating. It means those who replied differently are not serious with question. Okay, I think I gauged the class situation. So next, please. Thank you for the feedback. Okay, then I will play my slide. I'll come on that. So I tried to gauge what you think. Okay, that made my work easy. Why we are here today? My role is to talk about crop simulation modeling, a tool for climate change impact assessment. So what we will do today, we will talk about little bit of my background, then I will come on research background, what are the research outline I am doing so that we can collaborate, and then I will come on the climate change impact assessment. Okay, so next please. I will talk about my background, then the research background, why I came into this area, what I am doing, why crop simulation model is important, and the number 5th, after lunch. Overseas admission opportunities, after lunch we'll do that. And then we'll have question at the end. So next please, we'll go with my background. You see next, you see map on your right side. Next, yes. The maroon border is rice wheat ecosystem. You know, Indo-Gangetic Plain. And the dark maroon is my home state, Bihar. Next please, where I am from, north of Bihar, Madhubani, where I did my schooling from Navodaya Vidyalaya, Madhubani. After schooling, next please, I moved to Banaras Hindu University, BHU, for my undergrad. Next please. And you know, Rave and experiential learning, we were part of agriculture engineering group, so that's why I major in agriculture engineering. After my BS, I moved to IRI for my master's program. Next please. In environmental sciences, focus was on agriculture, physics and climatology with crop modeling. Then I moved to PhD, next please. For crop and soil sciences, focus was on crop and climate modeling at Michigan State University. Between my master's and PhD, I had 6-month gap because time frame of admission is different than in India. Next please, then I work as SRF in Indian Institute of Soybean Research in Indore for 5 to 6 months before my PhD. After doing PhD, I joined as a postdoc at Kansas State University with agriculture experimentation. Next please, after 1.5 year of postdoc, I joined as a associate scientist in USAID lab, Feed the Future Innovation Lab. And this year, in the beginning of this year, I joined as a Mississippi State University. That is my background, and I will talk about research background. Please, next please. So research background, this is the photo. How many of you know about NICRA? NICRA. Okay, 1, 2, 3 or 4 person know about NICRA. National Initiatives on Climate Resilient Agriculture is a great project on climate resilient agriculture. NICRA. So I was a student in NICRA with Dr. Himanshu Pathak. He is now DG of ICR. So he was my supervisor with Dr. Surya Naresh Kumar, 2 advisors. During that project, I was involved in mung bean, how to assess drought impact on mung bean. But during 6 months of my work, next please, I moved to soybean and I started working on water deficit stress with Dr. P.K. Agrawal. If you know, Dr. P.K. Agrawal is in CGIAR system, CCAF, Climate Change Agriculture for Food Security, blah, blah. So he is now scientist there, IBMI. So I work with him and Dr. Surya Naresh on crop modeling. In India, popular crop model is InfoCrop. InfoCrop is a tropical and subtropical condition crop model. There I worked with him to develop water deficit stress modeling, and that paper came into field crop research. Next please, and that another paper came into another journal. So this is the first time in crop model, the field condition different stages were simulated in the crop model. So soil moisture simulation, and first time someone correlated with crop physiology. Next please. So in the crop physiology, you know the temperature difference and water use efficiency, how drought is correlated with that. So first time we did that. Next please, in the lab which is called National Lab for Simulation in IRI right now. In the center, Dr. Surya Naresh Kumar is the director of that lab. This is the first time the drought stress came into the modeling for tropical condition and subtropical condition. Next please. This was my master's work. Then I moved to US for my PhD, and what I did in PhD, I will talk about that. Next please. In PhD, I was part of team called Harvest Program. How many of you know about NASA Harvest Program? AgMIP or NASA Harvest. Those who are in modeling, they know. NASA is agency, you know, right? Space agency. So NASA has a program called Harvest where they assess the climate change impact assessment using models. So a group called AgMIP. How many of you know about World Food Prize? World Food Prize, right? So 2 years back, Cynthia Rosenwig received World Food Prize. She was a crop modeler. She received 2 years back. So in that one, I was a part of generating crop genetic coefficients. Those who in physiology or plant breeding, they know genetic coefficients. Genetic coefficients are traits of any variety which helps in simulating crop growth and development. That trait can be identified through field data and softwares. So the gene-based crop model, any varieties which was developed in the lab can be calibrated into crop models. So that was my role. Next, please. If you see the map, this is a map of Michigan where I did my PhD. And if you see the yellow one, that is a seed trial locations, variety trial locations in Michigan in different districts. We call it a county there. We collect data based on growing degree days differences because variety distribution relies on growing degree days. You know about growing degree days, right? So what we did, we collected 3 basic data: planting date, flowering date, and maturity, physiological maturity, along with the yield and yield components. Using those data, we developed a tool called NMCGA, Noisy Monte Carlo. Next, please. Next. So that tool is in environmental modeling and software called Noisy Monte. Next, karte rahiye. Next. Bas. So these 2 tools were used in different conditions. Noisy Monte Carlo genetic algorithm tool, where breeders try to test their G into E into M interaction in models, gene to crop models. Next, please. Next. So this is the first time this Noisy Monte Carlo genetic was used in crop models. That was my PhD first year work when I developed a lot of genetic coefficients for crop cultivar, and the tool was called Noisy Monte Carlo genetic algorithm. That brought attention of NASA Harvest program that expression of genotype coefficient is good, but what if there is a stress condition? So we need to run the model in abiotic stress condition during heat or drought. And that's how I came into another program in NASA, EcoStress. Next, please. Next. NASA EcoStress program, where they evaluate crop variety on a stress condition, drought. So how you will evaluate it? Evaluate those varieties on different stress condition when you will measure evapotranspiration. Measuring evapotranspiration means how much water is coming from soil and plant surface. Satellite can do that because of thermal cameras, thermal sensors. Now, they have, this is a flux tower, you know EDICO flux tower, EDICO variance tower. So we established through Ameri Flux Network. America has a flux network across the US to validate the satellite product. Satellite has a sensing of evapotranspiration. We validate through EDICO variance if it is correct or not. So I was part of Ameri Flux for corn, maize, entire maize ecosystem of US. There we estimated a lot of evapotranspiration models and validated because NASA has, European Space Agency has, ISRO has different models, their own models. IMD use own model for climate forecast. NASA use own model for their weather data. NOAA use another model. So every model has their biases. What we did, we ensembled means made an average. Average can be done by simple averaging and the Bayesian averaging, if you know Bayesian averaging. So that's what we did. Next, please. So we did ensembling of all models. If you see at the x-axis, the color-wise, the first one is ET flux, which is station, and those are different evapotranspiration from different models. You see the variation, the crop season variation. And these are the crop season from May to October for Michigan condition and most of the Midwest in US. So what we did, we assembled ET, and the last green one is the average one, Bayesian average one. For farmers, we sent those average ET data to use for irrigation. How they do? For any irrigation scheduling tool, when they use sprinkler irrigation, they use crop coefficient, KC. That is developed by FAO, 1998 paper, very popular paper for irrigation water requirement. And that was developed in 1998, but not specific for area, climatological conditions, crop condition, turbulence on the agrometeorology in the field condition. So getting crop coefficient from remote sensing, that's what we did. What we did, we designed crop coefficient for all crops in different field using inverse algorithm, getting estimate of evapotranspiration, remote sensing, and the weather station. When you take ratio of those, you will get crop coefficient. Next, please. That crop coefficient was used for irrigation scheduling. Now, across the Midwest, farmers are using scheduling tool, irrigation scheduling tool. In that tool, see the vertical red line, that is number of irrigation. They were using FAO-KC, and now after satellite, we see the line numbers were 7 irrigation in a crop season. They skipped 2 irrigation. Next, please. If you compare with different scenario, the farmers were using 10 inch per acre. When they use satellite data, KC derived, that is satellite data work, 6 inch, 4 inch per acre. Average farm size of the farmer is minimum 1,000 acre in the US. So 4,000 inch water in a crop season, one farmer, can you guess in entire US how much it will convert into money? The NASA Open ET program, they like that product. And entire California, Irrigation Valley, Nebraska irrigation, everyone, they are trying to integrate crop coefficient into irrigation system now. So that was another area. But when we talk to farmers, they said that that is the back story. Everything is done. But what about next 7 days, next 15 days? Then we jumped into climate forecast. Next, please. Seasonal climate forecast. How many of you knew about seasonal climate forecast or weather forecast? Okay, 1, 2, 3, 4. In your mobile, there is a weather app where you see next 7 days, right? That is mostly weather forecast. Seasonal climate forecast have two components. One is 90 days, one is 15 days. 15 days is mostly called S2S, seasonal to sub-seasonal. And seasonal is 90 days. IMD have news that this year there will be 30% above normal. What is meaning for farmers? Farmers ko to pata nahi chalega kya hai, right? Then what they will do? They will go to extension agent or meteorologist to get to know about their field condition. So what we did, for farmers, we downscale. Downscale means for temporal or spatial downscale, there are two components. Downscale on daily basis. So if there is a forecast on 15 days or 90 days, we downscale into daily basis. Next, please. And that tool, next, please. Precipitation and temperature, P and T, combined downscale. Next, please. And that tool came into use by USAID. You need to just put the value of below normal, above normal. Model will do the background. Okay, that's good. Thank you, sir. No, नहीं काम कर रहा. नहीं काम कर रहा. हाँ कर रहा है. आपने क्या किया? नहीं मेरा नहीं कर रहा. Anyway, so what we found कि आप उस पर डाउन स्केलिंग वैल्यूज डालें. मॉडल विल डाउन स्केल ऑन डेली बेसिस यूजिंग ए FRE sampler and the background is DSAT model that design irrigation scenarios and management scenario for fertilizer. That was my third objective of PhD. So model development first, stress condition, and then for forecast. All three combined, farmers were used for combining remote sensing models and climate forecast. Next, please. Next. Abhi farmers, now they are using farmers climate forecast tool. How they use? They know that condition, crop condition in the field, if you are growing maize, you know when will be the silking stage. How you will know before season? You will predict phenology using crop models, using regression curve. If you know phenology and if you know climate forecast, it will be warm or dry, you can manage disease. That is called disease early warning system. That is my core research in the, in next few slides, I will talk about that. How? If you know that there will be dry or wet condition, there will be disease development based on temperature and humidity. Most of the disease has threshold value of temperature 28 degree, humidity 80%. If you know those factors, you can predict early warning system, not controlling. So that's how farmers are now using. So I will come on that. Next, please. So I explained in the beginning weather outlook, seasonal to sub-seasonal, and seasonal climate forecast. These are three areas where you work on. Being an agronomist or a meteorologist, you need to decide what weather outlook you will use when, in the planting, pre-planting, mid-season, or end of the season. And that tool we used already for irrigation and fertilizer design process, irrigation scenarios, fertilizer scenarios in different stress conditions. Next, please. So there was my PhD work. I finished my PhD, next karte rahiye. Next. As my PhD committee, when I defended my PhD, I moved to Kansas State for postdoc. Now modeling to field work, next. What I did in my postdoc, most of the temperature response curve, optimal temperature, suboptimal, supraoptimal for varieties. Mostly I work with wheat and millets. So crop change, but abiotic stress work. With Dr. Vara Prasad, you know P.V. Vara Prasad. I worked with him, he's a world-renowned crop ecophysiologist. I worked with him to develop temperature response curve for varieties in millets and wheats. So there we did a lot of experiment. Now what is the role of those experiment if we cannot translate into field practices? Next please. During that work also, I work in next geospatial analysis. Next, I developed this tool. So back. Yeah. This tool, if you scan QR code, Android and iOS, you will find any tool or any technology, how it is sustainable. When I say sustainable, for an example, I am agriculture engineer. I develop a small robot or a small machine which is used by male, female cannot use that. So what is the sustainable use of that technology? I gave one example, any example can be possible. Because when I was working with Bangladesh team, there we were using weeder, handhold weeder. महिलाओं के साड़ी में फंस रहा था वो. Then feedback came that female cannot use that. Think of smallholder farmers in Africa. We were talking about conservation agriculture, reducing tillage, leaving stubble. एक लड़की आई मुझे बोला उसने, how I can walk in the field, I don't have slipper. हंसने वाली बात नहीं है. अफ्रीकन कंडीशन में स्मॉलर फार्मर्स के लिए फैंसी रिसर्च इज नॉट ए गुड थिंग, ground reality. So what we develop a sustainability assessment tool where you can assess on different domain. If you go to the app or tools, you can change your metrics indicators or you can design your own metrics and indicators, how it is feasible for long term. So that helped me in getting new position, associate scientist, and that I worked in Africa. Next please. In Africa, I started working in Senegal and Burkina Faso in nationwide development of drought monitoring. So how drought monitoring and forecast can help, we all know, right? Making decision from sowing to planting and other management strategy. Next please. You can downscale through state-wise, country-wise and district-wise, and then consult with development officer or extension officer to contact to the farmers. Oh, thank you. ये सिर्फ लाइट के लिए है. नहीं, नेक्स्ट करने वाला नहीं है, सिर्फ पॉइंटर है. That's fine. Okay, then leave it. And then what we can do as extension or as a policy makers, these decisions can be used, root zone soil moisture, drought indices for changing management strategy, sowing window, planting conditions. That helped in developing this monitoring and forecast for all African countries. Right now, my PhD student is working on developing this for all countries. So this is one project. Next, please. I will share the slides. So these were the paper. Next करते रहिए. Next. These were the paper came from those research background. Now, next, what I'm doing right now at Mississippi State. And that's how we will collaborate. If you are doing in those areas, and then I will talk on crop modeling after lunch. What I am doing right now, so that we can collaborate. I am doing in 4 domains. One by one I will speak. Next please. My team is working on developing overall, next करते रहिए, geospatial natural resource management combining with modeling and decision tool, plus next, we call it a SOAP, simulation and on-field participatory research. So we do experiment on the farmer's field, not on our experimental side. We get data from the field, feed into the crop models, and that's how we feed into the crop models to generate crop growth and development simulation scenario. And my lab name is called MAC Lab, Mississippi Agroclimatology Lab. So that is my lab. What does my lab do? Next, please. First one, this is a map of Mississippi. Next. We are developing Mississippi Growing Degree Day portal. It can be feasible for Maharashtra, Telangana, any state. What is the meaning of Growing Degree Days? Growing Degree Days help you in selecting cultivar variety, best variety fit to that climatic condition. First thing. Second thing, market risk. Because when you go for market, you plan after planting. Okay, इस साल मेरे को क्या होने वाला है? Based on yield, you plan that where I will sell. Maybe mandi, private agencies, harvesting farmer network will come to purchase, depending on that. And the climate risk. During season, if you know growing degree day projection, how you will know that. So let's give a demo. Next, please. There is a small video where you can see there is a portal where farmer have portal, and whenever the farmer go to their field, What they need lat long. And if they go to the lat long, click that any field, they can create GDD graph of their field, how GDD is growing up. Last 30 year, 40 year, you can compare with that GDD graph. You can select different crops, you can select different varieties, how it is responding through heat. Because heat is a major factor for phenology. जितना रोटी खाएंगे उतने बॉडी बनेगी. सेम प्लांट में वही जितना हीट आएगा उतनी बॉडी बनेगी प्लांट की, बायोमास बनेगा. That's why it is used for growers for selecting varieties and other conditions. Next please. This is one area we are working for different crops, for different variety. Another area I already spoke about irrigation, how we manage irrigation. For Maharashtra region, this is not applicable, so please don't go for that. This is for sprinkler irrigation, satellite based irrigation, those who do for 1,000 acre, 10,000 acre, 5,000 acre, for them. So if you want to validate evapotranspiration, that can be done for Maharashtra, but for irrigation transform, we cannot do. This is for satellite based data. So this is another area we can collaborate on, ensembling evapotranspiration. Next please. These are my partners. This can be done for Maharashtra, where we generate crop coefficients. What I spoke, crop coefficient means calibrating variety or calibrating crop models, and that can be done through blind and full calibration, step by step, evaluating G into M, and that can be done in any state for any variety, because we compare with different tools with field data. Tools like genotype calculator, glue, that is optimization curve, NMCJ, what I spoke about. So this area we can collaborate on. Next, disease prediction warning system, where my team is working on developing disease early warning system, where we can develop based on different threshold. As a plant pathologist, they provide us information that, let's say for ear rot, temperature 28 degrees is a threshold, humidity 80% is a threshold. That information only we need from plant pathologist or extension expert in plant pathology. Then we convert into the logical framework. Whenever it crosses, it gives, next please, it gives flag of this is state map. For each district, each county, each block, you can downscale and send to farmers the severity of disease based on climate data. And this can be done for Maharashtra also, so we can collaborate on that as well. Next. This is overall view, next please. This is overall view of my lab. So on top you see the climate work, irrigation work in the middle, crop modeling with a SPAR technology, and plant pathology. Overall work, what I do. And these are my collaborators, where we work with pathologists, breeders, physiologists, remote sensing experts, they work with us. These are our collaborators for different grants. Next please, these are the grants we work on, USDA, NIFA, NASA EcoStress, NOAA Weather Program Office, and MAP program of NOAA. Under these grants, we work on these basic research program. So this is overall I'm doing, and our lab everyone is doing, and we can collaborate on that. Next. Wait. Okay. For any agriculture research, we need 5 P. If you are a breeder, if you are a pathologist, if you are a agronomist, you need 5 P. First goal is to enhance productivity. You can collaborate with breeders, soil scientists, wherever you want to work, to enhance input use efficiency, to enhance productivity. That is first P. Next P is protective, means protection from abiotic or biotic stress. Anyhow, entomology, weed science, pathology, they work on that. Third P is prescription, prediction. How we predict, like meteorologists, soil scientists, agronomists, they work on prediction. What will be the scenario, climate change, impact assessment. Next please, third is prescription, extension. They go to the farmers and they talk on how much to do. Fertilizer, irrigation, pesticide. So most of the grants, we focus on these 4. But what is the missing 5th P? Next please. The practice, how much your technology goes to the farmers. Any random guess how much variety is developed per year from a single university? Any random guess? Maybe hundreds? Any university develop hundreds varieties in a year? More than that. But how much it goes to the farmers and they cultivate that variety? 5% at the max? More than that? National level, I don't think so. If Parvani is doing more than 5%, that's great. national level 5 to 10% maximum variety is adopted by farmers. That is called self-research. Self means S-H-E-L, Godrej, Almira. Varieties developed, you got promotion, you got papers, that's it. They do not reach to growers. For example, wheat. Entire India, 60% of the wheat area is developed by one scientist, Dr. G.B. Singh, who is a director of NBPGR right now. He developed variety. He's 2 or 3 varieties in 60% of wheat area. But we have more than 200 wheat breeders in India, major wheat breeders. So think of your research, if your 5P is promising or not. Why I'm telling that? When you write research paper or collaborate on grants, you need to think of these 5P. If we are targeting a global picture of global climate change, food, in need of food, fuel, and fiber, and can we address these combination of at least 3? In any research, if you have combination of these 2 or 3, you are doing good research. So that's why we will talk on crop simulation modeling, how it will help in that. Shall I continue, sir, or after lunch? Then I will talk on crop simulation model, how it helps in these kind of research. If you are okay, I can continue. So after lunch, then we'll talk core on crop simulation modeling, research opportunities, collaboration opportunities, and then we'll talk on how to get into US schools for PhD and postdocs. Okay? Next, please. Next. लंच के बाद करेंगे इस पे हम लोग बात कि क्रॉप सिमुलेशन मॉडल्स कैसे आपके रिसर्च को एनहांस कर सकता है. Any questions so far before lunch? Before lunch, any question, random question, any? During lunch also, थाली के साथ साथ गाली. चले? Good. Any question? कुछ भी पूछना है बताइए. नहीं? भोजन करेंगे. क्या बोलते जेवण झालेला जेवण करायचे और हो गया तो जेवण झाला. ओके ओके. I know little bit words. कुठे आहे? My roommate was Marathi in PhD. Any questions so far? No, then we'll go for food. Okay? Thank you.
So, thank you very much, Dr. Prakash Kumar Jha, for giving the very good workshop and lecture during this what are the climate models, how we have to use the climate models, and he has shown very quick response in which area we are interested, what is the level of our understanding, what we have to do in next class. That also you have seen, and the 5 P's of the agriculture, agroecology, because agroecology, GDD is very important, and on that basis we have to define the crops which are in the USA, because I have seen that one the duration of the soybean, sorghum, as well as whatever the crops grown like corn, they are having the more mature days as compared to our India. Yes. So the varieties are having, those are matured from 130 to 150 days, as well as in sorghum also it is taking more. Your sowing time is, I think, April, May. April last to May, and harvesting in the November. So this is a more than 6-month crop is there. But in our area only we are maturing the crop, soybean crop in 3 months only. Cotton is taking more, pigeon pea is taking more, but the soybean, we are having the varieties, and we are very pioneer in the soybean varieties like MAS 158, 162, they are maturing in 100 days only. and they are getting higher yield also. But what I have seen, the average yield of our and there in USA, it is more because ultimately the duration is more, yield will be more. And we are having short duration varieties, so yield will be less. So depending on the GDD, how many days are required for the maturity, yields are defined. So thank you very much, sir, for giving this very nice lecture on climatology. Thank you, thank you. There will be lunch break for 1 hour. 1 hour, okay. So we have to assemble here at 3 o'clock. Okay. Thank you. Thank you very much.
I think after lunch, the session will not be boring. So please feel free to have lavish food.
Yes, thank you.